Hi everybody, this unit that we're starting is actually called Modeling Geometry. So we're going to be modeling different parts of geometry, things that we have already learned, like circles and parabolas and parallelograms and rectangles, but we're going to model those on the coordinate plane. So the first thing that we're going to start with is coordinate proofs, which are going to deal mainly with your parallelograms that we learned earlier. As a refresher, we need to be aware that this top formula is the distance formula, and the bottom formula is the midpoint formula. Alright, so what we're going to do is we're going to put things on the coordinate plane, certain points, and we have to determine the shape that it is. When we do that, we actually create something called a coordinate point, a coordinate proof, okay? Basically, it combines what you know about geometry with the use of algebra. And what I mean by that is that in geometry, we learned about parallelograms, rhombuses, rectangles, squares. We learned about all of the properties of those things. But we're also going to use our algebra skills and using the distance formula and the midpoint formula to prove that certain shapes are what we say they are. All right, so for example, let's start pretty easy, okay? We need to make a square with a side length of 6 units. It doesn't say where to put it. I can put it anywhere that I want to. So one of the easiest ways to do this is to actually put one of the vertices at the vertex 0, 0. So then we can go up 6, and from the origin again go to the right 6, and then we go up 6 and right 6, and there we go. We have a square with a side length of 6. So let's draw our square. All right, and we can very easily prove this. We can show that this is a 90-degree angle. We can show that all sides are 6 lengths long using the distance formula. All right, now our next goal is to position a right triangle that has the leg lengths of 2 and 4. Now we know that the x and y axis meet at a right angle, so let's use this as our right angle. We can then take one side, make it 4 units long, and then the other side is 2 units long, and there we have our right triangle with a leg of 2 and a leg of 4. We could have also gone up 4 and to the right 2. So there were actually 2 different answers that we could make for this particular problem, either the black triangle or the red triangle. Both of those were right triangles with side length of 2 and 4. So now that we actually have the figure in the coordinate plane, we can use slope, we can use distance formula, and we can use midpoint formula to figure out if the triangle that we drew is in fact a right triangle. Just as a refresher, remember that the formula for slope is y2 minus y1 over x2 minus x1. So that's one of the formulas I should have included at the beginning as well. Alright, so let's actually get into the proving part. We have a rectangle ABCD with the following ordered pairs 0, 0, 4, 0, 4, 10, and 0, 10. So the first thing to do is plot the points. So let's plot the point 0, 0, 4, 0, 4, 10, and 0, 10. And let's connect those dots. All right, there we go. There is our rectangle in the coordinate plane. Now that we have our given information, let's take a look at what we're trying to prove. We're trying to prove that the diagonals bisect each other. So I'm going to draw the diagonals. Remember, there are 2. And one of the properties that we learned about rectangles is that the diagonals will bisect each other. So our goal is to find the midpoint of each diagonal. If they are the same, then they bisect each other. So I should have labeled A, B, C, and D. Alright, so now what we're going to do is find the midpoint of line AC. Okay, so we add our x values. A has an x value of 0, C has an x value of 4, so 0 plus 4 over 2. Y values are 0 and 10. So the midpoint of AC is 2, 5. All right, so let's extend the page a little bit, keep working. All right, next we need to find the midpoint of BD. So I have 4 plus 0 over 2 and 0 plus 10 over 2, and I get 2, 5. Notice that they both bisect each other at the same point, 2, 5. That means that they bisect each other because their midpoints are exactly the same. Alright, so let's work on the next proof. It says, given a right triangle ABC has vertices 0, 6, and that's A, 0, 0 for B, and C is 4, 0. So let's go ahead and connect those points. All right, and it says D is the midpoint of AC. So let's go ahead and find the midpoint of AC. So A is 0 and C is 4, and A is 6, C is 0. So the midpoint of AC should be 2, 3. So 2, 3. That should be point D right here. Okay, so now that we have all of the given information plotted on our coordinate plane, let's go ahead and prove that the area of triangle DBC is half the area of triangle ABC. Now remember that the area formula of a triangle is 1/2 base times height. So let's go ahead and find the area of triangle ABC. It's 1/2, and what's cool about the base is I can just count 1, 2, 3, 4. And the height, just count again. 1, 2, 3, 4, 5, 6. So what we have here for the area of triangle ABC is 12, and we're just going to put units squared. So that's the area of triangle ABC. Now it's our goal to find the triangle of DBC. So we need area of DBC. So it's still 1/2 base times height, okay? It is our job now to find the area of the base and the area of the height. Now, if we take a look at this triangle, I need to drop an altitude down from point D. So this would be our height of 1, 2, 3, and our base would be 1, 2, 3, 4. So I get 6 units squared. So what we have just shown is that the area of DBC is half of ABC, since 6 is 1/2 of 12. All right, so our proofs have been dealing with specific cases. Given a certain point, prove this. However, we can actually use a general idea to prove that it will work for any, so for example, let's talk about this rectangle that we did. We proved that for this particular rectangle, the diagonals bisect each other. But if we gave this a variable and said this is going to be our rectangle, we could prove it for any possible rectangle. So with coordinate proofs, you can prove for a specific case, which is what we've been doing, or prove that it's always true. Now, when you do that, though, we have to leave it as variables. So if I have a rectangle with a width of m and a length of twice the width, this is what my triangle is going to look like. Oops. It has a a width of m and a length that is 2 m's. So from here to here, I went up m units. From here to here, I went over to the right 2 m units. So the missing point is 2m, m. Okay? So this is how we write a general rectangle. Okay, we could have done anything like 3, whatever. So let's go ahead and write a general rectangle, or excuse me, a right triangle with the legs of S and T. The first thing you're going to do is you're going to start with your coordinate plane. And the reason I'm starting with the coordinate plane is because it says a right triangle. And I know that a right angle occurs when x and y meet. So let's do the length of s. So let's say s comma 0. Oops, it looks like a 5. S comma 0. And then up to t. Oops, 0 comma t. And this would be our triangle. Now remember, there's actually another way that you can do this problem. What if it had been up s and over t? It would still be a right triangle with the length of s and t. And this is in fact what it would look like the other way. But make sure you are only using the origin and the axes if you have a right triangle. That is very crucial. Alright, so position a square with a side length of 4p in the coordinate plane and give the coordinates for each vertex. I want you to pause and give this a shot now. So the first thing that you'll need is an x and y axes. So with the side length of 4p, it means we'll go up 4p and over the same distance 4p. And then we connect our dots. So the first point is going to be 0, 0. The next point is 4p comma 0. The point up here is 0 comma 4p, which means that this right hand corner here will be 4p comma 4p. Alright, so given any random rectangle, I need to prove that the diagonals are congruent. This is what I mean by saying we can take a general rectangle and prove it for every case rather than a specific case. So the first thing that we're going to do is we need to position and put this in the coordinate point. Let's go ahead and start with point S at 0, 0. From P to S, let's from S to R, let's say that we go over a unit. So that would be a comma 0. From S to P, we need to go up a different number. We cannot go up A units over A units. We have to go up B units because a rectangle does not necessarily have equal sides. It can in a square, but it could also be 5 and 4. So we have to make sure that we have different variables, so that way we have different lengths. And this right here is A comma B. So that was step 1, is to put it in the coordinate plane. Now, step 2, we have to write the actual proof. Alright, so what we're going to do, we want to know the diagonals are equal in length. So let's use the distance formula and find the distance from SQ. So let's call this x1, y1, and x2, y2. So we have a minus 0 squared plus b minus 0 squared, which will simplify to the square root of a squared plus b squared. Alright, that's the distance of SQ. Now we're going to do the distance from PR. Let's call this x1, y1, and x2, y2. So we have the square root of a minus 0 squared plus 0 minus b squared. So we get a squared is a squared, a minus 0 is a, 0 minus b is negative b squared is still a positive b squared. So what do you notice? We notice that both the distance of SQ and PR, the two diagonals, are congruent. And because they are congruent, we can prove that the diagonals must be congruent for every rectangle. Alright, well that's it for today. I will see you guys later.